Hello everyone, welcome to our quick tutorial on z-scores. So just as a reminder, our z-score formula, the idea behind z-scores is that we're standardizing scores so that we can compare different distributions, even if those distributions have different kinds of scales of measurement, if they have, if we're dealing with some that are high numbers and some that are low numbers. This lets us kind of standardize those so that we can compare different groups and different populations. So this is our Z formula. All standardized scores or z-scores always have a mean of the z distribution of 0 and a standard deviation of the z distribution of 1. That is because they're standardized, right? That's the whole idea behind them. So to kind of go through what that looks like, on how we would calculate these scores. If we already have the mean of our distribution and we already have the standard deviation of our distribution, then calculating those z-scores really becomes pretty easy. So here are our original values, 1, 3, 3, 4, 4, 5, 5, 5, and 6. For that raw score of 1, we would subtract the mean of 4. That gives us a -3. We would then divide that by our standard deviation of 1.41, and we get a z-score of -2.13. We'll do the same thing for our value of 3. 3 minus our mean of 4 gives us -1. We'll divide that by our standard deviation, and we get a negative z-score of 0.71. Notice that z-scores below the mean are negative values. And so whatever that deviation score is on our numerator will indicate the whether the z-score is a positive z-score or a negative z-score. For our value of 4, this is the mean, right? 4 is our mean, so we don't have any deviation there. And so 0 divided by anything is still 0, and so we'll have 0 for those two values. Now our 5 is above our mean, so without even looking without even doing the formula, I can already estimate, hey, this is going to be above my mean. My standard deviation is 1.41. So I would expect it to be less than 1 standard deviation, a z-score that's going to be a decimal. And so I have a 1 divided by 1.41, and I get 0.71. Notice that our 3, our z-score for our 3 and our z-score for 5 are essentially the same z-score. They just have different, whether it's positive or negative. And that's because they're the same distance away from the mean. This is what z-scores is doing. It's standardizing this for us so that we can make those comparisons. And lastly, our 6, this is our most extreme value, or one of our more extreme values. 1 is our most extreme value. And so we're still going to have a z-score that's above 1. But again, if we have a positive deviation, it's going to be a positive z-score. If we have a negative deviation, it's going to be a negative z-score. Now, we can also go the other direction with all of this. As a point of note, if you're doing the entire distribution, your z-score should always add up to 0. And that's, again, because that mean is that balance point. Because we're doing those deviations, we're still going to add up to 0 in this case. Now we can, again, because we have our z formula, we can go the other direction. And we can get raw scores given a z-score. So how we would calculate that, if we have a mean of 4 and a standard deviation of 1.41, just like we did in our past distribution, what if we want to know about a score that we didn't have in the original distribution? What if we wanted to know what a z-score of 0.5 would be, a half a deviation away from the mean? And we can solve for that. We would take our 0.5 and we would multiply it by our standard deviation of 1.41. Then we would add that mean in, and we get a raw score of 4.71. We can do that for another example with a mean of 5 and a standard deviation of 3.74. Again, what does a z-score of 0.5 look like? Is a raw score there. And again, we can calculate that out. So 0.5 times our 3.74 plus our mean equals our 6.87. So that's how we calculate z-scores, and that's how we calculate raw scores from z-scores. So again, we can go back and forth. Thank you so much.